We'll wait. We're just at the top of the hour. We'll wait another minute or two and let people finish getting in, and then we'll get going. We have Iury Simoes-Sousa here today. I'm just going to talk about atmospheric cold pools in the Bay of Bengal. And I just want to wait a little longer to let people finish getting in. Okay, well, shall we go ahead and get started since we're already recording? Welcome to the Air Sea Fluxes from Space webinar series through OASIS. Today we have Iury Simoes-Sousa, who's going to talk about atmospheric cold pools in the Bay of Bengal. He's a postdoc at WHOI Oceanographic, and so he'll share work he's been doing. Thanks for being here.
Thank you very much for inviting me. I think that as we were discussing, it's very interesting to have those remote seminars, and it's awesome to be part of this community as well. So as Sarah mentioned, I'm now at postdoc at WHOI, but this is actually a work that I've done during my PhD at UMass Dartmouth. This is a very collaborative work. I have my advisor here, a former student from the lab, and many other collaborators for this project. So it was part of the Mesopub ONR project. So I have to acknowledge that. And this paper has been was submitted and published at Journal of Atmospheric Sciences. All right. So first of all, I like to say that I just came back from India, so I'm not really good with jet lag. I just found out that because I didn't know that before, and I went to India for this these 2 weeks for this geophysical flows lab workshop, and it was a very interesting experience, not only culturally but also professionally. So we had these workshop groups with students, and we taught students about how to the theory and also how to model gravity currents in the ocean using modern computational tool. And we also had 2 days of discussion, and I had the first time the opportunity to present this work in India. So it was a very interesting experience. And just another ad is that I walked more than 1 hour to reach the beach just to touch to the water of the Bay of Bengal, because I thought that was so important for me, because I had this chapter of my PhD that was regarding the Bay of Bengal. And I invite everyone to go there. I think that it's a very open lab, and the IIT Madras. I'm pretty sure that if you want to collaborate and participate in those workshops, they're gonna be very happy. All right. So why do we care about atmospheric cold pools? So first of all, cold pools are formed by mostly by the evaporation of raindrops. So the raindrops will evaporate and will cool down the surrounding air, that will generate these cold air pockets that will further, of course, by buoyancy, they're gonna sink and generate these downdrafts. And as they reach the surface, it will be just like if you spill water in a surface, it's going to spread radially, and this is going to expand just like gravity currents. So there is a theory here that you can use to investigate the expanding of these plumes. So they are characterized by temperature and humidity drops, because they have this they come from an origin that the air it's usually colder by the raindrop evaporation, but sometimes, and this depends on the conditions that you have at the surface, they're gonna also show a humidity drop. And of course, they're going to influence the heat fluxes, hence the latent fluxes. And as they expand, they can lift the surrounding air, and this mechanical lifting can reinitiate convection. So this is a side view of what a cold pool look like. So you have this very classic study that shows the cold air outflow. So this is what the cold pool will be associated to these mesoscale storms. And just as an example of how striking these events are, I mean, I was born in the tropics, and I experienced that so many times that I didn't have a name for that, but it's very classic. I mean, everyone knows when it gets very dark during the day, you have these gusts, and it gets cold, and then you have rain. So there is this sequence of events that happens usually during cold pools that people that live in the tropics, they know that this is going to happen. So it gets just as dark as night, as you can see this picture in the shortwave radiation. And this particular cold pool was actually a cluster of cold pools happening here, but you have a very strong temperature drop of more than 5 degrees in 1 hour. And this happened during the Iury cruise in the Bay of Bengal. And as you can expect, I mean, you have a striking rain happening during the cold pool event, and the wind is very variable during the events. So it's very gusty. But now the top view of a cold pool, they look like this. So you see that they form these arcs here. And you can see clouds forming in the edge of the arcs. And here I have a very weird scale of 34 kilometers, and there's a reason for that. So the reason for that is that this is the distance between the moorings that I'm analyzing this study. So we were very lucky to have 3 moorings. There were 2 NIOT Indian moorings and a Woods Hole mooring in the north of Bay of Bengal, and they are separate about 34 kilometers. And the idea here is that the scales of these features are larger than the distance between the moorings. So this is gonna be very important for us to do some analysis of particular events that are gonna happen in all the 3 moorings. So this is in the northern Bay of Bengal. And here I'm presenting the time series for the temperature. And there are many interesting features here. So this data is for the 2015. And what I'm showing here in blue is the 1-minute data. So it's the high resolution data. And I'm marking every time that you have a temperature drop of more than 1 degree per hour. So I'm kind of putting a die here for the all the cold pools that we see. And I'm also presenting here the 30-day running average just to have a sense about the seasonality. So what we have here is that we have the summer monsoon starting in May, and you see that these events start happening so many times during the summer. And what is very interesting is that they seem to drop the baseline of the temperature as well. So like you would expect that if you didn't have these events, maybe the temperature would be higher than 30 degrees. So one thing that we observe is that most of them happen during the summer. The other thing that we observe is that if we look at the zoom panels for 3 days in July, you see that these events happen in clusters, and they tend to happen in the same time of the day, which is very curious, right? And the other thing that is very interesting is that in the 3 moorings, you see the same events that are very similar happening at the same time. So like, for example, this one, you can see that it's marked just like in the first mooring, you see in the other mooring and in the Woods Hole mooring as well. So that gives us an idea that these events are being captured, the same events are being captured by the 3 moorings, right? Okay, so there are so many things that I mentioned here, but based on that, we define some scientific questions. So the questions are, what are the characteristics? What is their contribution to the RC fluxes, the total rain, as well their temporal variability and their high distribution. And some of these analyses I already presented just by looking at these plots, but we're gonna have to first automatically identify these events. And to do that, we borrowed a concept from actually topography, and this is called prominence. So the prominence here is the distance in terms of peak is the distance between the peak and the minimum value that does not enclose higher peaks. But in our case, it's in the opposite sign. So we are actually looking at negative peaks. And we first remove the 30-day running mean, and then we identified all negative peaks with prominence more than 0.5 degrees. And we only keep the peaks that have this sharp drop of more than 1 degree per hour. It doesn't need to last for 1 hour, the drop, but it has to be a very strong drop just for us to differentiate the DO cycle from a cold pool event. And here I'm showing some examples for a particular day, and we see that some events happening in the 3 moorings, but other events only happen in 2 of the moorings. All right, so we have all these cold pools identified, so now we can do all sort of analysis. So the first analysis that we do is that we can see that the cold pools, they are in the temperature time series, they are marked by a sharp drop and a slow recover. So most of the analysis of the duration of cold pools is done actually for the recovery time. Now, what I'm presenting here are cumulative distributed functions. So these are CDFs, and I'm marking here the median and showing the skewness here. The values for each mooring are in blue, and the CDF of the combined moorings is marked in gray. What we can see here is that the median is around 2 hours for the recovery time. Most of the events happen from 1.5 to 3.5 hours of recovery time, and they are substantially longer than equatorial cold pools. So there is a study from Simoes-Sousa in 2017 that shows that the median is around 0.5 close to the equator. They are also longer than cold pools in the South Bay. So there is another study from 2021 that shows the cold pools varying from 1 to 1.3, depending on the mooring that they are analyzing. All right, so there is some latitudinal difference here that we're gonna discuss a little bit. But the other question that we had was, what are the effects on the rain and heat fluxes? So here I'm presenting the precipitation from one of the moorings, the Woods Hole mooring, alongside with the IMER data here. So this is a satellite data. And what we can see here, I'm marking here in gray, and I hope that you can see that, all the cold pool events that happen in this time series. And what we can see here is that every time that you have a cold pool happening, you have this striking rain happening as well. And of course, I mean, it's hard to imply causality here, but what happens that 80% of all of the total rain happens during cold pool events. That's for the northern Bay of Bengal. And then another interesting thing is that the satellite data follows the same pattern, right? With 87% of percent correlation for the total rain, daily rain, comparing the 2 data sets. The other thing that we can see is that the sensible and latent fluxes are enhanced during cold pool events. They can even be 3 times from the base level. So they are definitely important for the heat fluxes in the region. And if we, the heat fluxes here are obtained by core algorithm, but if we simplify the heat fluxes as the bulk formula, we see that we have an importance of the wind, but also the interfacial differences of temperature and humidity. So the main question is that what is the role of the wind here? And if we look at the wind and the interfacial differences, we look at something like this. So it's not really clear if the cold pools are enhancing the wind speed, but they are definitely more variable during the events. And this is not true for all regions, but this is what is happening in the northern Bay of Bengal. So in the other hand, we see that most of the differences are driven by the interfacial differences of humidity and temperature. So based on that, we perform a series. We gather all the code pools, and we perform a series of composite analysis. Analyzing here, what I'm presenting are composite analysis for different properties, showing the median and the 20F to 80F percentiles spread. So we see here the temperature drop, median is around 2 degrees of drop, Celsius degrees. The sensible and latent fluxes are showing here the pattern that it's driven by the cold pools. And what I'm doing here is that I could perform the same analysis using core algorithm with a 3 days low pass wind or a 3 days low pass temperature and humidity. And what we can see here is that actually 9 to 10% of the sensible and latent anomalies are contributed by the wind. And this is really different from other results that from a study that was performed in Bay of Bengal. But what we can see is that there is a latitudinal dependency in the wind contribution. So cold pools in the South Bay of Bengal have more importance of the wind, and these cold pools that we are analyzing here, the wind is not as important for the enhanced heat fluxes. So another thing that we can see is that, as I mentioned before, we see a little bit of hump here for the wind speed, but actually the signature is more clear for the running STD of the wind speed and wind direction. And as we saw before for those that time series that I showed before, we see that the precipitation is definitely marked right at the temperature drop of the cold pools. And they show some signature in some influence in the surface temperature and salinity with a very broad spread. And of course, I mean, you see some influence in the shortwave radiation as well, and the relative humidity and specific humidity. So one thing that we observe here is that all cold pools that we observe in the Bay of Bengal are dry. And this is kind of expected for cold pools that happen over the ocean. All right, so the other thing that we did is that because the composite analysis will kind of smear out all the variability between the cold pools. So what we did was we took the difference between the different properties at the minimum temperature and at the maximum temperature before the drop, and we are plotting here the prominence of each cold pool for each of the properties. And this is important for us to understand the variability, and also I'm showing these values, this scatter plot of the prominence varying with months, so we can understand a little bit about the seasonality of these events. So many events happen have a more than 3 degrees of temperature drop, and we can see here from the prominence plot. The summer events can enhance the sensible and latent heat fluxes more than 25 and 50 watts per meter squared, respectively. And the wind is very variable, but not necessarily higher. So we see here that it's not really skewed, but the wind speed standard deviation and wind direction standard deviation is positively skewed. So it's showing that the cold pools are definitely gusty. All right, so the SST drops and SSS drops for some reason. This is something that we have not investigated very well, but we see that most of the most enhanced SST and SSS drops occur during from September to November. And this is not really when we have the most intense cold pools happening. And some of these SSS drops can be actually derived from just an artifact of the analysis that we are doing, because we can have river plumes happening in the Bay of Bengal, and they can mark the signature in the analysis that we are doing here. So our cold pools are dry, with many events showing more than 2 grams per kilogram of specific humidity drop, and most of them happen during the summer, these strong events. All right, so the other thing is the effect that they do for the rain. And here I'm showing a joint histogram of the for different times of the day and different months. And the color here shows, for the upper plot, shows the number of code pools happening in the analysis. And here is the total rain in each of the combination of time of the day and month. So what we see here is that the histogram of cold pools and total rain, they match. And this is kind of expected because cold pools are formed by major storms, mesoscale systems, and they can also drive rain. So but one thing that is very interesting is the DO cycle. You observe that most of the cold pools happen in the late morning. And the question is actually depends on this southeastern propagating storms that happen daily in the Bay of Bengal. So this study by Joseph and colleagues in 2021, they performed this Hofmöller from the TREM data. So this is a precipitation data derived from satellite. And they can observe that this propagating southeastern major storm, that it's the parent storm of these cold pools, that it's reaching different latitudes in different times. And from their analysis, most of the cold pools occur in the early afternoon. And that's for south of the region that we are studying. So we expect this occurrence of early occurrence of cold pools in the North Bay of Bengal. It's kind of expected. All right, so the other thing that we did, we tried to estimate a little bit about the height of the cold of the plumes from the cold pools. And here I have to be very specific. The height here is not the origin of the air pocket, but the height of the plume of this air pocket as it reaches the surface and expands horizontally. So here we are assuming, what I'm showing here is a very interesting plot from Van de Hive and colleagues 2021, and it's showing the gravity current shape that cold pools can have with the head and tail, just like we expect for gravity currents. And so what I'm doing here is we're gonna solve this equation for age actually. So if we assume that the Froude number is 1, we can actually remove the background wind and solve that for age. And the temperature here is the virtual temperature. All right, so what we did, we combined overlapping fronts. And so like if we assume that cold pools can move from 10 to 20 meters per second, taking the 34 kilometers, that is the distance between the moorings as a reference, a cold pool that moves at 10 meters per second would take a maximum 1 hour to reach another mooring. So this, and as most of 80% of the identified cold pools, it's shorter than this recovery, has a recovery time that is shorter than that, longer than that, we assume that this is a fair analysis. So we match 83 matching events. We had 83 matching events, and the matching events are only valid when it occurs in the 3 moorings. So like, for example, these events here kind of happen in 2 of the moorings, but not all of them. And this event here could be the same, but it by the time that it happens in the other mooring, it already recovered from the first one. So we are not, so some of the events, we are just assuming when they're occurring at the same time of the recovery from the first one. So what we did was, we did a little bit of geometry here, and if we assume that this is a straight front, taking the frozen field assumption, so the propagation during in this distance between the cold pools will be constant, we can assume that the propagation is the advection plus phase. And if we remove the background wind, which is a long-term, I think is a 3-day low pass wind, we can obtain the phase. And we solve for, we solve that to obtain the phase speed, taking the difference of the time delay between the temperature drops in each of the moorings. And what we obtain is something like that. So most of the cold pools are propagating to the southeast, and they have a very variable propagation speed, and this is from 4 to 20 meters per second. And this is actually in the same direction of the major storm. So we didn't use the wind speed here to estimate this propagation. So this is actually really assuring that we are doing the right thing. And if we subtract the wind speed, the background wind speed, wind velocity, we can obtain the phase. And based on the phase, we can estimate the height. And so here I'm showing the temperature drops statistics. This is the CDF. This is the CDF for the phase of the propagation of the cold pools and the respective height of these plumes. I know that there are many assumptions here that we are doing, and but this is the best that we can do from the 3 movings. And what we can see is that the height of the cold pools is from 375 to 2,200 meters of height. And the highest fronts occur from May to September, and they are higher than the level of the lifting condensation level, which is not really, I mean, the best way to do that, but it's an interesting fact that could relate to how strong is the relationship between the occurrence of cold pools and the rain in the Bay of Bengal. So we compare that to other studies, and we can see that actually these cold pools are not totally off, but they are higher than other observations from cold pools in the ocean. So there are some explanations that that could be investigated in the future, but of course there are some assumptions here that we are taking that might not be true for cold pools, but it's an interesting study anyway. So I always like to finish my presentations with a question, and I think that the main question here is how important are cold pools in reducing surface flux biases and the rainfall bias in the climate models. I know that the Bay of Bengal, it's a critical region. The monsoons, it's not really well represented in climate models, and maybe this is one of the ways that we should direct our studies, maybe finding better parameterizations for the cold pools influence, or understanding better about how they change globally. So this is my contact information, and I'm open for questions.
Thank you very much. This is great. Questions from the audience? So, and maybe while people are thinking of questions, I'm wondering, are there radio sound measurements to validate the height of the cold pool in any cases?
They are not radio sound measurements at this. I mean, at the same time that we had this data, so we could not really compare with that. But I think that maybe using I don't know if there are other campaigns, even if it's not in the same year, that launched radio sounds, because it would be interesting anyway, because we could use and try to compare that, but we didn't use for this study.
I think the other prospect is that there are satellite capabilities, for example, from the proposed butterfly, to be able to measure some of the vertical structure, and you're seeing a height that's high enough that it seems like it might be detectable.
Yes.
But there's a time of day question. So you'd have to think, what time of day would you really want your measurements in a sun-synchronous satellite?
Yeah, in that case, I mean, we know the time, because we know when they are happening, at least. So yeah, I think Nicholas has a question.
Yeah, Nicholas has his hand up. So Nicholas, go ahead.
Yes, thank you for the question. Thank you for the talk. I have actually 2 questions. The first thing is, you showed that there was no consistent impact on the wind speed of these cold pools.
Yes.
And I wonder whether you might be able, whether the wind speed response is actually sorted by the relative position of the cold pool with respect to the large-scale winds, whether it's upstream or downstream, in respect to large-scale winds of the center of the convective system. That's the first question. And the second question is about the SST drop and the SSH drop, seas over salinity drop. You looked at SST and seas over salinity. I wonder whether you do the same thing for rate of change and whether you see a more consistent picture.
Yeah, I didn't do for, I will answer the last question first. So I didn't do for the rate of change, and maybe it's a good idea. Yeah, I didn't do for, I didn't thought about that. But what I can see here is that there are some cold pools that, like for example, that showed more than half of grams per kilogram of salinity drop, which is really, really strong. I mean, I wasn't expecting to see. Of course, you can form these freshwater lenses due to so it's not really just I mean, it could be a case that these events are related to the highest precipitation anomalies, but I didn't find any relation on that, or I didn't investigate. Yeah. But and the first question, I don't really know. I mean, I think that what I could see here is that, and this is clear when you look at the time series, is that sometimes the wind is higher during a cold pool event, and sometimes it's even lower, the wind speed. So I'm not really sure. I think that when I look at the time series, and I did my best to not only rely on composite analysis, but when I look at the time series, I didn't see any strong, effect.
In your satellite picture that you showed earlier, that showed these arced fronts. These were, if I recall correctly.
So what you see is that there is a specific direction here.
Exactly, it's anisotropic. Exactly.
Yeah.
Yeah.
Yeah, I'm not sure. But I think it's an interesting thing to investigate in the future.
Yeah. Thank you. Thank you very much.
Yeah, no problem. Thank you.
I see that Megan has her hand up.
Yeah, hi. That's a great talk. Super interesting. I put in the chat a link to a paper by Samantha Wills where
I saw that. I think it was a very interesting paper. I cited. I actually had. I think I had a chance to. Yeah, I had a chance to cite this paper.
It's some of what you're doing is very similar with the impact on the fluxes. But what I find very interesting in what you're doing is looking at the height.
Yeah.
And so could you just
I wonder if you can also do the same with sail drones, right?
Yeah. So could you talk a little bit more about how you do that, and how robust do you think it is, and if you?
Yeah, I think that the robustness, and I mean, to be frank, it wasn't easy to put that in the paper. The reviewers didn't like much because there are many assumptions. But I think it's the best that we could do. So what we were doing is that if we assume, if we overlap the cold pools that are happening at the same time in the three events, so we first overlap them, and we have exactly the time of the temperature drop. So we take that as a reference. And taking the time delay between the temperature drops in the tree moorings, we can solve the geometry to obtain a constant propagation speed of a straight front. And actually, one thing that I can say that I did, I also ran Monte Carlo simulations. I didn't put that in the paper, but Monte Carlo simulations of cold pools propagating through the tree moorings. And the propagation speed that we obtained was, if we assume that they are straight fronts for this scale, was not. I mean, it was a good assumption. So, like, if we took the frozen field assumption, and if we solve for VP is the propagation of the plumes, and as Nicholas mentioned, they have this preferential propagation due to the major storm. So, to obtain the phase, we have to subtract the background wind. And here the background wind, I'm taking the 3-day running average wind, just because I noticed that there are clusters of code pools that can last for a day. So like if we subtract that, we obtain C, and we can solve. We have the temperature drop, we have the temperature reference right before a code pool. So we basically just solve that for age, and we obtain a sense about how tall they are. Yeah.
So that delta T, could that actually be done as a time rate of change of the temperature? So that's like your 1 degree drop?
Yeah, so the delta T is the temperature. If we look at the composites, yeah, they're gonna be the prominence. So it's basically the temperature at the the minimum temperature defined from the prominence algorithm, the minimum temperature and the maximum temperature before the minimum temperature. So this temperature difference here is the delta T, and T0 is the temperature before the cold pool event. So it's the reference temperature before cold pool event. So it's related to each of the cold pools. Yeah. And there is a time delay between the events. So I think that for sail drones, as the temperature drop is so fast, I think that you can use that with sail drones without having to take into account the movement of the sail drone, because it happens. Most of the cold pools, it's 1 hour of temperature drop. So,
but I guess, I mean, can you go back to that equation with the C?
Yeah, I think we are assuming that they are gravity currents. So we are assuming here that that
the spreading out of the plume,
yes,
that's the gravity current.
Yes. Yeah. So
okay.
Yeah, there are some studies that they show that they are not. Yeah, so one thing that you have to take into consideration is that to assume a Froude number equal to 1, you have to remove the background wind. Otherwise, they're gonna be super critical. So the Froude number will not be 1 because they are forced. But in our case, we remove that.
So that delta T, I mean, so that's kind of like the reduced gravity.
Yes.
And so the delta T here is actually a stratification.
Yeah, so the delta T is the and it's the virtual temperature. So it takes into account the humidity as well. So it's it was confusing for me as an oceanographer, but it's a temperature that it's sort of a potential density variable, because it takes into account the pressure and the humidity as well.
So you have to know
anything wrong.
You need to know the H to do the pressure of that temperature, right?
We had pressure sense. We had pressure sensors, so we use that to estimate T. Yeah. So T is taking.
So have you compared this at all to profile measurements?
No, we haven't. So I think that this is this is a very interesting breakthrough. I mean, something that can happen after that. But we didn't have the opportunity to compare with radio suns because we didn't have radio suns in the same time in the same region. But I think that now that we have the distribution of the height, if we have radio suns happening in the measurements in the Bay of Bengal, we can try to compare that and see if the distribution is the same. So I think that at least that will provide some idea on how well was the assumptions that we are taking here. The other thing that I think it's very interesting that could be done is that, so we could see that satellite measurements could mark the cold pool events, some of them. And IMERG data is not very easy to handle because of the resolution, of course, but I think that would be interesting to take a look at and see if we could observe that even for those smaller code pools. Because usually when you look at the satellite, it's when they have expanded, and so yeah. So I think that's one of the things that would be interesting to investigate, and also the latitudinal dependence. So we believe that this is probably related to the evolution of the parent storm. Let me see. Yeah. So as the parent storm moves, we expect that the temperature difference will be, so because of the dissipation, the temperature differences will be smaller. So the cold pools will be more dependent on the wind than on the temperature. So that's one of the gas that we have, but we didn't investigate that in deep. So the cold pools that happen in the northern Bay of Bengal, which is closer to the origin of these storms, they're gonna have a more contribution of the interfacial temperature and humidity differences than contribution from the wind. But thank you for the questions, and I think that Samantha's work it's awesome.
Yeah, she is now a program manager at COM, so she's kind of doing a pivot in her career.
Other questions? Roger Samuelson has his hand up. Roger, go ahead.
Yeah, thanks. I'm curious, the cold pools, they're associated with rain, but you also said they were dry, and I guess that's specific humidity. Could you just say a little bit more in detail about the relation between the rain and the humidity and the temperature, how it works?
There are two mechanisms that cold pools can generate rain. One is mechanical, which is the mechanical lifting. So as they expand, they're gonna lift the surrounding air. And as I showed from my measurements, they are taller than the lifting condensation level. So that means that they get this surrounding air and they lift higher than the lifting condensation level. So they can generate rain by this mechanical lifting. But the other thing is that they are usually dry, and as they expand, they form these high humidity rings. So in the surrounding, and with this higher humidity in the surrounding, and that depends on the surrounding air. You also have this. I don't remember exactly why they are formed, but as they are formed, with more humidity, the air will be more buoyant, and then so you have both the thermodynamic and the mechanical lifting mechanism that can generate rain. But some of these analyses actually, and this is one of the things that I discussed with the reviewers. So we cannot really assure causality here. So some of these rain might be due to the major storm, actually. That is just coincidentally happening when you have a cold pool. So not all the rain that it's coming from the major storm is evaporating, and some of this rain is happening at the same time that you have the cold pool expanding. But I thought it was really striking that 80% of total rain happens during cold pool events, and we can see this marked in the composite analysis that the peak of the precipitation is right at the temperature drop, which corroborates with the idea that the cold pools are expanding and mechanically lifting the surrounding air. But thank you for the question. Yeah, I think that these I mean, when I started studying atmospheric cold pools, it was pretty new to me. I didn't know much about that, and actually it was very interesting to be an oceanographer and have a paper at a journal of atmospheric sciences, and I came across many times I had different concepts. For example, people talk about, instead of height of cold pools, they talk about depth of cold pools, and it was really counterintuitive for me as an oceanographer. So I can understand that some of these concepts might be not really yeah for us.
Okay, thank you. And so is that, so if you look at that precipitation distribution there, is that consistent with, measurements of similar features over land? In other words, in that schematic that you had at the
I think
beginning.
this is a very good question. I'm not sure, but I think so. I don't remember on the top of my head the distribution of the precipitation in relation of cold pools with rain, but this is actually, most of these studies on atmospheric cold pools are in land, not in the ocean, because it's, I mean, of course, it's, you have way more observations, and this influence of cold pools in the rain, it's well described since the beginnings. So I think that this is also observed in the land. I just don't remember exactly any plot like this. But I think it's a very good question because, for example, in the land, you can have some wet cold pools. So it all depends on the conditions that you have at the surface and the conditions that you have at the origin of the air pocket. So they are defined by the temperature drop, but not necessarily by the humidity drop. And as you have when you have a wet surface in the land, or in the case of the ocean, you will always have a more humidity close to the surface than from the origin of the cold pool. So what happens that all cold pools that happen over the ocean, they are dry. So this is just a matter of relative comparison of the humidity.
They're dry from the point of specific humidity, but they're wet from the point of relative.
Yeah, because the temperature is low. Yeah.
Yeah. Okay. Well, that's interesting. It may be a misconception, but I have always thought of cold pools as sort of running out ahead of the major convection and rain. And so this looks different to me, but I don't really know much about that. So
yeah, me too. I'm just learning.
Other questions? I guess if I can ask one further question, I'm thinking hard. Well, I see Gwendal has his hand up, so I'll let him go first.
Okay. Hi, Iury. That was brilliant. Thank you very much. I have two questions. First question is, what kind of measurements do you have with your buoys in your Bengal area?
Yeah, we have meteoroceanographic measurements. I don't remember all the variables. I'm showing here some of the variables, but maybe if you're more specific to what kind of property you have in mind.
So my question is, I think we can see a change of surface roughness because of the presence of the cold pool from radar image, I guess. And my question is, do we see some signature of the cold pool? So it's kind of out of the scope of your talk, but I'm curious about it. Do you think you have signatures of the cold pool if you have wave measurement with your buoy log? Because you have a change of the wind velocity, perhaps you can change like the wind speed, or do you think like the change of the wind speed is not enough long so that the wave doesn't really respond?
It's a very short term event. So I'm not sure, but I think I'm not sure, but maybe, yeah. I think it's something that requires investigation, but I never heard of this actually. So maybe it's something to do in a future collaboration.
Okay, thank you very much.
Yeah. Okay.
I think Gwendal set up my question nicely. I've been thinking about what you can do from satellite, and of course, the issue with most atmosphere observing satellites is they're on sun-synchronous orbits, so you just get measurements at 2 times a day, but these clearly have a spatial structure. Do you think you can translate the temporal evolution you've looked at into looking at, say, the appearance of a front in wind or waves or temperature?
I think this is one of the key questions. I was thinking about how to observe them using satellite measurements before. And I tried to do, I actually didn't include there here, but I tried to do a little bit using iMerge data, but I didn't think about trying to extract that from surface measurements. But I think it's a very good idea. I just haven't thought about that in the past.
Yeah, there's clearly, because this is a timescale that's very difficult, except from geostationary satellites, and maybe that has potential. There's clearly an opportunity to do something creative. It would take a little thought.
Yeah, I think that the only problem is how you can be sure, just like my height measurements, how can you be sure that you're doing the right thing? You know, like if you don't have enough observations. And I think that cold pool, it's a kind of a very multi-scale. There's a very strong multi-scale interactions here, because we can see that it definitely changes what we expect to see during summer monsoons, because as you have higher temperature, you would expect to have more humidity, and it kind of gives a negative feedback that because you have higher temperature, you have more these storms happening, and you're going to have more cold pools happening, that it's going to generate these humidity drops. So I think that it's very interesting, but at the same time, it's such a short scale, both in time and space, that it's really hard to make sure that you're doing the right thing. You don't have a benchmark.
Yeah, clearly there are plenty of ways to do the wrong thing. By, say, measuring at times of day when you completely straddle the events, missing everything and just seeing their net impact, and you could infer all sorts of other things. Well, are there other questions? Nicholas has his hand up.
Just to follow up on Megan's question about this height of these cold pools that you measure from the gravity wave speed. You mentioned in passing that you also have pressure observations. Couldn't you combine your air temperature, perturbation, and the pressure to get another estimate, an independent estimate of the height of these perturbations? Hydrostatic pressure?
Yeah, I haven't thought about that. But yeah, it could be something that it could be done in the future. Yeah, it's very interesting. Actually, it's very interesting to give a presentation to this group, because I wish I had given this presentation before publishing the paper. Now I have so many good ideas to pursue in the future. Yeah, I haven't thought about that, but maybe it will be hard to separate the effect of the cold pools from the major storm in the pressure. I'm not really sure how to do that.
Thanks.
Yeah.
But wow, that would be super useful if we could use surface measurements of pressure and air temperature to get information about heights of these kind of convective events.
Yeah, definitely.
Yeah, even very rough estimates would be helpful, wouldn't they?
Yes. Yeah, I think that the whole idea was, because I mean, inland people are doing James Bond operations, like Van der Heever group. So this data, I didn't show much about other things, but they have the radar, but they also had a curtain of drones that was flying in the aligned with the front of the cold pool to measure temperature in different heights and have a sense about the vertical structure. And of course, I mean, you can try to do these things in the ocean as well, but operationally it's way harder, because they had these vans, and they had the drones in the vans, and they were tracking the cold pools from the van and driving to the leading edge to make the measurements. And this is not really possible to do in a short time in the ocean. But I think that it would be interesting to any measurement of the height of them, and would be really helpful. And there are some studies from the same group that have shown that even if you use a very high resolution of a comparison between 150 to 200 grid spacing, changes the vertical structure of a cold pools and their effect in the surface fluxes. So I think that having a sense about from observations on how what are the characteristics length scales and influencing the RC fluxes, it's really important for making sure that the models are doing correct.
Mm-hmm.
Yeah.
Well, if there are no further comments, we're almost at the top of the hour. Thanks for a really wonderful presentation, a great discussion.
Thank you very much.
Thank you.
Thanks, everyone.
Mm-hmm.